This is the traction suitability. So several rapid cutting movements, non-standardized, just the perception, what is the best suited traction condition, questionnaire, traction suitability. We had then a lab test, biomechanics, for cutting. We chose to go for a 45-degree cutting movement because it is the movement that we identified from our game analysis. We already heard some comments. We did a notational analysis a couple of years ago because that is the movement that happened the most often in a game, more than 45 times per player. 5 repetitive trials, and as variable, I would like to show you the force ratio, medial-lateral shear divided by the vertical. The mechanics, cutting simulation. What we found important is for cutting simulation is to cut off the upper. So we just put the outsole on a wooden block, as the upper would add some instability and therefore some randomness, which we wanted to exclude. And the variable was the loading rate max, and we had an angle of 10 degrees. So we had the whole sole, 10 trials, speed driven, and we applied a load of 750 Newton. So testing procedures, we had a subject pool over the 3 years. We had 4 different shoe models, randomization. We had a FIFA 2-star certified artificial turf. Statistics, relatively simple, mean standard deviation, repeated measures, ANOVA, and a post hoc test according Bonferroni. So what were the shoe conditions in the status quo evaluation? And this is basically reflecting the situation we were at. We had a new surface, but we had the old natural grass shoes. We had hard ground design, normally used on frozen or very hard surfaces. Then we had the standard firm ground design and the standard soft ground design. Those two, firm ground and hard ground, were those that were currently used on artificial turf, currently because that dates back to 2007. We also had some kind of prototype. First prototype, well, footwear company is always interested in putting in some new technology. That was called dual cell technology. This is, well, people come up with these ideas, but they still do not know whether it's functional or not. This was the first round, and what I would like to point out at the beginning is the mechanical traction that we measured, and for the soft ground design, we had highest mechanical traction. The cut force rate, newtons per second, was clearly higher than for the hard ground, firm ground, and for the innovative design, that's what it called here. So when we see the firm ground was slightly higher, and between the hard ground and the innovative design, no difference almost. So we had high mechanical traction for the soft ground model, which we should keep in mind when going on. When we now come to the athlete testing, well, involving players with movement adaptation, with movement variability, we see a different picture. We see that for the slalom running time, this slalom parcours took about 10 to 11 seconds to be completed. We see that the soft ground shoe had the slowest running time, meaning the worst performance. And the best shoes were the hard ground design and the innovative design. When we come to the player's perception, how they feel about it, then we see that they were pretty much reflecting, in this case, the objectively measured data, that they perceived the soft ground design to be the slowest one and the firm ground to be the second slowest one. And same traction suitability, this was unsuited. People may find this, well, this is trivial, but when you look at kicking velocity, for example, we have carried out studies that show that players' perception not necessarily reflect objective measurements. So basically, perception and actual performance need to be treated as two different things. Here, it's a perfect match, which we are, well, which from our point underlines these results. Interestingly then, when we look at biomechanics, we see that the soft ground design has the lowest force ratio, medial lateral force by vertical force ratio. And this is, from our point, interesting. When we go back here, mechanically, this is the highest traction, the soft ground, and when we then go here to the biomechanics, we have the lowest traction variable. So, what we found out is that soft ground design less suited. This actually gave, in a way, illustrated why players do not or did not choose the soft ground model when playing on artificial turf. Now we have found out about the reason why that is the case. However, we also know that the hard ground is better suited, and this, for whatever reason, innovative design was better suited, and the firm ground design was fairly suited. It is quite commonly used on artificial turf. It had a little poorer values than this one and that one, but still was fairly suited. So based on those findings, we could go on with phase 2, having educated prototypes based on the knowledge we found out. What I would like to draw your attention to is what I've already touched about, the difference between mechanical and biomechanical traction. So we are talking about mechanical or mechanics as the availability of traction. Mechanics can show us this is the potential availability of traction, and it's basically due to interface characteristics like material, geometry, and loading. What kind of loading you apply? We had 750 newtons. However, we also found out that the utilization of traction by the player is different. This is due to the athlete with specific anthropomatics, with specific body composition, when we can think of maybe male-female comparisons, having a different muscular fat composition of the body, being leading to different things of stabilizing, for example, the knee. Also, motor performance skill and the current training status need to be taken into account. So basically, these are different things, what is available and what can be utilized by the athletes. That is, that optimization of traction is necessary in order to maximize performance. It's not a maximization of traction, it's an optimization of traction. So, this is basically what we found out for this, from this phase 1. I will go through phase 2 and phase 3 now a little quicker, just to give you the idea of what this 3 years project was about. So we had new prototypes when we, in a way, tried to come up with a better dual cell technology, and we also put this dual cell technology at the rear foot. So this was the carryover from phase 1, and now we put the dual cell technology at the forefoot and the rear foot, and we played around a little bit with the hardness of these little dual cell technology studs. We have here all those analyses, performance, biomechanics, and perception, and what we came up here with is that slalom running time was only slightly better for the dual cell 90 prototype, which had the hardest dual cell elements. But what we also see is that here the picture is for the dual cell 90, it's okay, but here we have some differences that are not reflected here. Traction suitability, again, pointed in the direction, even though not significant. And what is interesting, so in terms of biomechanical force ratios, we do not have any differences anymore, which might be overshadowed by the movement variability. So, very slight differences, nevertheless. So, we found out no negative effect of rear foot dual cell compared to rear foot firm ground, and we had no effect or no big effect of slightly different TPU hardness that we had here. Nevertheless, we need to make a decision, and that's why we made a decision. We go with the descriptive statistics and pick this one for the second or for the third round. And this was then the market comparison. A problem you have with the market comparison is that you that you are only able to come up with a market comparison with the shoes of the competitors that are already on the market. So it's not a very valid market comparison in terms what will be released in the next year, but still we included this one as a Puma shoe at that time. So we included the current Puma shoe model to challenge our own product, but also Adidas and Nike, commercially available for 3 major brands. And what we see here is that the innovative design was still faster, was perceived better, and here what you can see, even though not only, but significant, not highly significant, it allowed players to have a better push-off, a better biomechanical force ratio. Traction suitability was perceived to be the best. But this is the biomechanical, let's say, evidence. Wearing this boot, players were able to evoke a higher, a bigger, a stronger push-off. So the final prototype outperformed the commercially available artificial turf shoes. That made us happy at that time. But also, rather than just picking this boot, we were able to derive general manufacturing guidelines. And this is shorter and evenly distributed stud configurations were identified to provide better suited functional traction to players. That it seems that on artificial turf, the shorter studs are better suited than these relatively long studs, and that multiple studs are helpful for quick and agile movements of the players. So what we did in this study is we based our analysis about footwear mainly on clear and direct performance variables, meaning running time, slower time, better performance, and also a direct variable to perception. If a player tells us the shoe is better, the shoe is faster, then is better suited, then this is very direct and interpretation is very easy. With most of the biomechanical variables, interpretation is not that easy because they are indirect. So what do we know when there is a higher moment, a higher knee angle? As long as we do not, or as long as we cannot relate these variables to performance, we, in most of the cases, need to be careful with the interpretation of these indirect biomechanical variables. So, in this study, we analyzed different stud configurations, and we found out that they cause movement adaptations during a soccer turning movement. So the objective, and we did this in cooperation with Liverpool John Moores University. So some of the setup is quite familiar. I can go through this right quickly. So biomechanical analysis of a 135-degree turning movement, wearing soccer shoes with different stud configurations, hypothesis, loading differences due to footwear are present, and kinematic movement adaptations should be observed. This is basically what we did: approach speed monitoring, and then 135-degree. 2 kiss to 4 plays and a motion capture system. This was the tracking, the marker setup with anatomical markers and tracking markers. And the protocol, again, 5 repetitive trials, randomization of shoe models, the 4 different shoe models I will show later on, and 15 experienced and, in terms of anthropometrics, regular subjects. These are the shoe conditions we used, and they are really familiar: soft ground, firm ground. This was the kind of final prototype of the artificial turf shoe, and then we included a kind of academic situation. We removed all studs of one soccer shoe, basically of this shoe. We removed all studs to have a no-stud boot. Well, obviously nobody is proposing this to wear during a 90-minute game, but from a research perspective, you are able to derive some interesting things from that.